Good morning. This is your stats sensei, Mr. Spensey, and we are going to do a hypothesis test for a t distribution. And what makes it a t distribution is that we will be working with the sample standard deviation. If we had the population standard deviation, this would have qualified for a z distribution, but because it's the standard deviation is coming from the sample, this will be a t. So a medical researcher is testing a new drug to determine whether or not it slows the growth of malignant tumors in rats. That word slows is going to be really important. The average growth rate for this type of tumor in rats is 6.2 grams per week. Okay, so we know that this is some sort of mean. The new drug is tested on 30, so we have our sample size of 30. So that's easy to identify. So there's our sample size. Selected rats out of a study of 500. So we have a total of 500. So this is less than 10%, and that takes care of the 10% condition. For the rats treated with the new drug, it was found that the average rate of growth for the tumor from the sample was 4.1. All right, so average, that tells me I'm looking for that's a mean, and this is from the sample. So 4.1 is my X bar, with a standard deviation of 2.8. Also from the sample is my standard deviation, so this is 2.8. So the question is, what's my population mean? Well, they already told us that it has an average rate of 6.2. So that is our status quo. So they want to know if it slows it, that means it wants to decrease it or make it less. All right. So let's write our hypothesis. HO mu equals 6.2. And what are we measuring this in? Grams? Yes, 6.2 grams. And our alternative is mu. This is always going to be the same number. Everything's the same except for the inequality. Remember, this is always equal. But here it says slows, so we're going to be less than because of that slows. Our formula, T equals X bar minus mu S divided by square root of n. If I were to draw a picture of this, which we need to, it just helps make sure that we actually have a good look of it and a good understanding. Our picture is we're going to be centered on 6.2 because that's where we think we are. That's where we've been. But we got a sample of 4.1, which is further down here. And it's specifically a one-tailed test, and I was looking for it to be less. All right. So let's go ahead and start plugging our information into our equation. So that we want the probability that t is less than 4.1, that's our X bar, minus 6.2, so our sample mean minus our population mean, divided by our sample standard deviation, and that's divided by the sample size of 30. And remember, we would need 30 in order to check normality. So, stat, test, number 2, t-test. We have statistics. There's our mean of 6.2, our sample mean of 4.1, our sample standard deviation of 2.8, our sample size of 30, less than is highlighted, and we calculate it, and we get a t-statistic of negative 4.1079. So the probability that t is less than negative 4.07, negative 4.1, excuse me, 079 is, and let's look at this real quickly. This has e to the negative fourth. That means it's 0.000149. Remember, we can never have a probability greater than 1. So as soon as we do that, get one that looks like it is, we need to make sure that we check to see if it's written in scientific notation, and this is. So 0.000149. All right. So our p-value is 0.00149. Has 4 zeros. There we go. And we're at the 2% level. That's our alpha. So 0.02. And here I have 1, 2, 3, 4. I did that wrong. I'm going to rewrite this. 0.0000149. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And that's a much larger number. So this is less than. And whenever our p-value is less, we have to reject the null. Now we need to write a conclusion and put this in context, but for right now, we just wanted to do the computation. I appreciate you watching and hope to see you on the next one. Thank you.